So let's get started. So today we are going to do a bit of a recap on the grand canonical ensemble. What was the key idea? Last time we studied how to get averages from grand canonical ensemble. We will look at that again very slightly. And mostly we will focus on number fluctuations. So grand canonical ensemble, you can control the number of particles, right? So if you can control it to have an average value, it means it's going to change from it every once in a while, right? So what is the fluctuation? What is the variance? And then we'll talk about this Gibbs entropy concept, which you have probably seen if you have taken StatMech ever. That's how they derive things earlier, but we will see why it's consistent with everything. And this will really mark the completion of first part of this semester, which is the basics of StatMech. Towards the end of today's class, we will start with the second part, which is introduction to non-interacting ideal systems. So that sounds like the most useless thing ever, right? It's ideal and it's not even interacting with each other. Why should you care about it? But you'll see it can make, basically we will talk about a little bit of quantum statistics. And it won't be all quantum, it will be classical also. So, and we will see even how non-interacting ideal systems can lead to very, very rich behavior. For example, black body radiation or heat capacity. So we will talk about all these things that end with ons, phonons, photons, fermions, boson, electrons, all of these. And that will take us a little bit of time to work through everything. And once we finish that, then we will move to part 3 of the course, which is really non-ideal systems, which are also interacting with each other. That becomes very hard, but that is life, right? Life is none of you are ideal gases, right? Maybe you think you are, but you're not, right? You're not a point particle. You do not, if you collide into someone, it's not elastic most likely. So, and you all interact with each other. So life is really non-interacting ideal systems. But if we develop the machinery for, life is interacting non-ideal systems. If we develop the machinery for non-interacting ideal systems, then we can think about interaction as a perturbation on top of it and develop systematic ways of dealing with it. So this is the way going forward. And the part 4 will be some more advanced topics. We will do a little bit of phase transitions like Ising models and some renormalization group, and depending on how much time we have left. And one thing to keep in mind is that March 9, Thursday, there is no class because I have to sit on Zoom all day, which is terrible. And March 13, Monday, there is an extra class on Zoom in the evening, whatever time I wrote on Slack. You can go and check. And I also sent a calendar invite. So this is March 13, Monday. March 14, Tuesday will be regular class. And I want to make a point due to some reasons that March 16, Thursday class will not be on Zoom. It will be only in person. It will not be recorded. It will not be on Zoom. So it will follow Chandler very, very closely, but March 16, Thursday's class, you should attend in person. I'm letting you know in advance, okay? That will be the last class before the spring break. That one will not be on Zoom or not be unrecorded. Vedant, are you listening?
Yep.
Good. So let's get started. So again, no discussions about the midterm. I won't even ask you whether it was type 1 or type 2. We will respect Alex. And I think I'll have fun grading it. Let's see. So let's talk about grand canonical ensemble. What was the idea in grand canonical ensemble? We had a system which could exchange not just energy with its environment, but also number of particles could go in and come out, okay? And in order to study what is the probability of a microstate inside this thing, how does a microstate will be characterized by the energy of that microstate E nu and number of particles in that microstate P nu, right? And we showed that this probability is proportional to e to the power minus beta E nu minus mu and nu. You should pick up your homework. And I said a bunch of things about the future of this course. So check it out in video and in the notes. So I'm surprised when I see Omar in class. I don't know why. No comments. So, and so that is proportional. And then if you want to remove the proportionality constant, that is 1 by z e to the power minus beta e mu minus mu and nu, and z is just so that the thing is normalized. So Z is summation over microstates e to the power minus beta E nu minus mu N nu. And this Z depends on mu. What else does it depend on? Huh?
Depends on beta.
Temperature and volume, right? Beta or temperature. So it depends on all these three. And in order to derive this, we looked at the system embedded in a bigger bath, and we considered that the bath is isolated. So this was bath, this was system. I want to make a mathematical point here. Most of the time in statistical mechanics, you will see Gaussians. When you do your expansions, probability will look like a Gaussian, e to the power minus something squared, right? These probabilities are not Gaussians. These probabilities have not a square dependence, but they have a first order dependence, right? Why did this happen? Any ideas? Why did we not get a second order square term here? Why do we have a first order term in these probabilities? And how do we get Gaussian out of a Taylor series? By ignoring the first term, right? And why do we ignore the first term in a Taylor series? That is true here also. We ignore the first term because it is close to an equilibrium, right? And we say first term signifies some sort of force. And if you're close to an equilibrium, the force goes to zero. If you're close to a maximum, when we did this derivation, we were not talking about maximum, right? We were doing Taylor series where N nu was much smaller than N. So we kept the first order term. It was a dominant term. The first order term did not disappear. We were left with it, right? So keep that in mind. So we had P nu, and we derived similar expressions for the canonical ensemble. And for the microcanonical, we didn't have to do anything. That was our starting point. That was our ground. That was the first and the main assumption we made, that in a microcanonical ensemble, if everything is isolated and you have constant NVE, then all microstates are equally probable with condition given that information. So the equation to remember is this one, that P nu is equal to 1 over Z e to the power minus beta E nu minus mu N nu. So this is the grand canonical probability. Last time we showed that N bar. So since we are imposing a constant chemical potential mu, N can fluctuate, right? And we derived the value of average N, and that turned out to be 1 over beta partial ln Z by partial mu. In your next homework, which won't be out until next week, some point next week, and you'll have enough time to do it, you will show this in your next homework, which will be homework 3, that the average value of the energy is minus partial, and this here we have to keep constant V and beta, or V and T, and you will show that average value of the energy is this same derivative of the log of Z at constant mu and V. It has another term over here, and similarly you can derive the average value of the pressure, which is going to be 1 over beta partial ln Z by partial V. In your homework 3, I will, and if I don't ask you in your homework, the probability that I ask you this question in your final or somewhere else becomes even higher. I would like you to think about P bar for ideal gas. And I would like you to think about P minus P bar whole square for ideal gas. So what do you expect the answer should be for an ideal gas, the value of P bar? nRT by V, right? Ideal gas law. What do you expect for the second one? The fluctuation in an ideal gas. How much should it be? Yeah. Even simpler. What's the simplest number you can think of? 0. It turns out to be 0. And I will give you this on your homework or your final. It's 2 pages of algebra to do that. That the variance, and it's only for ideal gas. For a non-ideal gas, you will see fluctuations in pressure. Okay, so that's quite interesting. I was not going to do it, but then Garrick told me at dinner last night I should do it. He said he gives Garrick Papoyan. When he was taught this class, he gave it, and it was 2 pages of algebra. So that sounded great. But the result itself is interesting, and it's going to show up later, okay, in your homework or something. So go and try it so you're ready. So I will do something similar. I will derive a similar equation, not for the pressure. I will derive it for the number fluctuation. Okay. So what I'm going to do next is to think about how the standard the variance in N. How does this look like? And I want to make one more point, which we did last time, which is of course very important, which is the connection of Z with thermodynamics, right? So we showed that omega G is equal to minus KT ln Z of mu Vt, which is the same as minus PV, right? Omega G is equal to minus PV. So this is something also we did last time. So this was all a recap. Now get to new stuff, which is to think about the variance in N. So we calculated variance in E, remember, for the canonical ensemble. How did that look like? So recap, we did sigma E square for NVT ensemble, right? How did sigma E square depend? What, I don't care for the final expression, but what was the dependence? What did it depend on? Anyone remembers? The variance in energy in a canonical ensemble. Don't go so fast.
CV.
Okay, and what does CV depend on as a function of N? Is CV intensive or extensive?
Extensive.
Extensive. So it depends on N, right? It's order of N. So going to what Nathan said, if I want to think about the standard deviation in energy divided by the average in energy, that will go as square root of N divided by N is equal to 1 over square root of N, right? This was a very striking relation, that the noise, which is the standard deviation divided by mean, goes as 1 over square root of N. So as N becomes infinity, noise over mean goes to 0. We are going to see the same thing over here. We will see that sigma N square divided by N bar, square root of sigma N square, the standard deviation of N divided by the mean of N, also goes as 1 over square root of N as N bar tends to infinity. Which means if you are going to use a grand canonical ensemble to calculate the average number of particles, the number of particles will fluctuate, but the fluctuations will become smaller and smaller with respect to the mean. And this all happens due to central limit theorem. That's why it's keep happening all the time. So let's try to derive it. So in order to do this, what do we have to show? We will have to show that sigma N is proportional to square root of N, right? That's how we will get that. So this is what we would like to show. We would like to show. Okay. How should we proceed? What is the definition of the variance? The definition of the variance is average of the square minus that's average of the square minus square of the average, right? That is the definition of the variance. This is not StatMech, this is statistics, right? That's how variance is defined. You can do it more carefully. We did it last time, right? You can define it actually as the average of N minus N bar whole squared, and you see this is what it comes down to. Remember, we did it for energy. That's the same idea. So now I need your help. Which of these two terms, let's call it equation number 1, which of these two terms have we already calculated in terms of the partition function? Second one. Which is this equation, right? Let's call it equation number 0. So equation 0 says N bar is equal to 1 over beta partial ln z by partial mu at constant volume and beta. We haven't calculated average of n square, right? We need to calculate average of n square. In statistical mechanics, anytime we want to calculate average of something, how do we do this? Average of n square is going to be, go to every microstate, write down the thing that you want to calculate it, which is n nu square, multiply with the probability of that thing, okay? What should I do next? Nick, what do you think? What machinery do we have to proceed here to help us? Absolutely. Did I number it? I did not number it. So let's call it, well, there's no way. We have to call it equation number -1. Yeah, there's nothing wrong with it. Why hate the negatives? So use equation -1. Okay. So that will be n nu square. And what is the value of p nu, Nick?
Z times
E to the power
negative beta divided by e mu minus
multiplied by E nu minus mu n, right? So that's the value. Let's write down this equation on the next page. I'll write down the full thing on the next page. So Nick says, and if it's wrong, Nick is to blame, sorry. Average value of n nu square is equal to go to every microstate, look at n nu square multiplied by p nu. And we know that this is go to every microstate n nu square, and p nu is e to the power minus beta E nu minus mu n nu divided by z, right? Z is constant. Z does not depend on every microstate. It's already summed out. So we can put z outside. And the same operation that you have done a few times is going to show up again. Think about what should you differentiate with respect to. This is n nu square e to the power minus beta e, sorry, let me write it down in full. E to the power minus beta e nu e to the power plus beta mu n nu. So this is the step in StatMech that unless you do it a bunch of times, it appears as a bit of magic. So first of all, you're talking about square, you're talking about fluctuation. So you should already be mentally ready that you are going to get a double derivative, right? The job won't get done in one derivative. You will have to go to double derivative. But let's think about the first derivative. What can we hope to pull out of a derivative? Is this thing n nu square, right? So let's try to pull out the first n nu. In order to pull out the first n nu, differentiating this thing is not going to help. There is no n nu over here, right? This is the thing that we have to differentiate. So let's try to work through it. So let's do a back of the envelope calculation and think about it, that if you were to write down e to the power plus beta mu and nu by derivative with respect to mu, what would we get? We would get beta n nu e to the power plus beta mu and nu, right? So you can see how that can be written. If you are willing to take one of these n nu and introduce another beta, then you get the job done, right? So let's write it down as 1 over z summation nu. Let's keep one n nu over here. Let's keep e to the power minus beta e nu over here. And let's introduce beta n nu divided by beta, right? Because there was no extra beta. I'm just doing algebra over here. And then write e to the power plus beta mu and nu. So if you look at all of this together, beta and nu multiplied by e to the power plus beta and nu, that is exactly what we had here, right? Right? This is the same thing. Therefore, this can be written as 1 over, and this beta can be brought out, 1 over beta z. We will pull this out. Summation nu n nu e to the power minus beta e nu partial derivative of e to the power plus eta e to the power plus beta mu and nu by partial mu. Okay. What can we do next? Any ideas?
Try to
Go ahead.
write by mu again.
Do we need to? There is actually another shortcut here. When you are differentiating with respect to mu, what is the behavior of this thing? It's a constant if you're differentiating with respect to mu. So now you can do something. The double derivative will actually show up in a sneakier manner. You can keep this nu over here, and you can take this thing inside here. This thing can go inside here because that does not depend on mu. It's a constant. So this thing will become derivative of e to the power minus beta e nu, e to the power plus beta mu and nu by partial mu. Okay. Now something's happening. This is 1 over beta z nu n nu partial by partial mu e to the power minus beta e nu minus mu n nu. Okay. And this whole differentiation with respect to mu can be brought out outside the sum now. Because you're doing it in every microstate and summing it up, you can do it over the full sum together. This becomes 1 over beta z partial by partial mu summation over nu n nu e to the power minus beta e nu minus mu n nu. And now the final trick I'm going to do is to multiply, divide by z inside here. Okay. I cannot put z outside. I cannot take this z and bring it inside over here. Why cannot I do that? Z depends on mu, right? But inside the derivative, I can do whatever I want. I divide and multiply by the same z. If I do that, we're almost there. This becomes partial by partial mu z summation nu n nu e to the power minus beta e nu minus mu and nu by z. Is there something familiar here? What is this thing? That's n bar. We just got n bar once again inside, right? So what did we just show? We just showed that n nu square is equal to 1 over beta z partial with respect to mu of z n bar. I'll stop for a moment. It's a lot of algebra, and unless you have seen it before, it's terrible. It's like, yeah, it's like, where is the chemistry here? Where is the physics here? This is just like terrible high school algebra. But the manipulations here are very typical in StatMech. You know, differentiate with respect to what, multiply, divide with respect to what, and you have to practice to develop intuition. Okay, which equation were we at? We got to equation number 1. Let's call it equation number 2. Okay, everyone okay with me moving to next page? Okay, so let's move to next page. Let's write down this equation once again. So we just showed equation 2 was that average value of n square, we don't need to keep writing n nu square, it's implied what we mean, is equal to 1 over beta z partial by partial mu of z n bar. What are we keeping constant in this partial derivative?
T and V.
T and V, right? Z depends on mu v t. Remember, it's like we are working in a mu v t ensemble here, right? So anytime we are differentiating with respect to mu, the things that are being held constant are vt. So we have, the algebra is unfortunately not done. We have to keep doing a little bit more, but it's not too bad. Now we will actually do this product derivative. This product, we will apply product rule on this derivative, okay? So what's that going to look like? That's going to look like keep z outside and do partial n bar by partial mu plus keep n bar outside and do partial z by partial mu, right? Both of them keeping volume and temperature constant. Okay, we are finally starting to get somewhere. Let's bring this outside. So this first term will z and z will cancel from numerator and denominator. What are we left with? We are left with 1 over beta partial n bar by partial mu plus 1 over beta n bar 1 over z partial z by partial mu. Okay, stay with me. 1 over beta partial n bar by partial mu 1 over beta n bar partial ln z by partial mu, right? Anytime we have 1 over x dx, we can say d of 1 over x, d of log of x, right? It's a product rule. So we have this thing. Okay, well, what is this thing? Remember the formula for n bar? The formula for n bar, equation number 0, equation 0 said n bar is equal to 1 over beta partial ln z by partial mu. So partial ln z by partial mu is actually beta multiplied by n bar, right? Therefore, partial ln z by partial mu is equal to beta multiplied by n bar. So if we go to equation number, let's call this equation number 4, put 4 in 3, what do we get? Average value of n square is equal to 1 over beta partial n bar by partial mu plus 1 over beta n bar multiplied by beta n bar. So beta beta cancel. We get n square is equal to 1 over beta partial n bar by partial mu plus n bar square, or variance of n, which is defined as the square of the standard deviation of n, which is defined as average of n square minus square of the average, is nothing but 1 over beta partial n bar by partial mu. And this is the key relation. What does this tell us about the order of magnitude of variance of n? Does beta depend on n? Is beta intensive or extensive? Intensive. Is chemical potential intensive or extensive? Aiden, what do you think?
Intensive.
Intensive. Is n bar intensive or extensive?
Extensive.
It's as extensive as anything is going to be, right? It's like saying, is Aiden Aiden or not? No, you are Aiden. You know what I mean, right? N bar is like the extensive thing. So what does this tell us about variance of n? Extensive. Extensive divided by intensive, right? Therefore, variance of n is extensive. And extensive does not mean order of n square or order of n cube. Extensive means order of n, okay? Is order of n. So we got the same thing we got for variance of energy. Just like variance of energy was extensive, we got variance of n is extensive, okay? And this immediately leads to the thing we wanted to show. If variance of n is extensive, what does it tell us about the standard deviation of n? That is square root of n, right? So I will wait for just a moment. Okay. If variance of n is order of n, then standard deviation of n is order of square root of n. So then standard deviation of n by average value of n is order of square root of n by order of n, or order of 1 over square root of n. So we get the same 1 over square root of n dependence here, okay? And it shows up all through in statistical mechanics. If you are doing an experiment on anything and you keep making more and more measurements and your standard deviation by mean is not behaving as 1 over square root of n, if n is large enough, that means you're out of equilibrium. Something is going on in your experiment. You did not equilibrate it, which should be the nemesis of most of us, whether we are doing simulation or an experiment, right? Because equilibrium is our guiding principle. If you're out of equilibrium, there is only one way to be in equilibrium. There are many, many ways to be out of equilibrium. Is anyone apart from here, apart from Alex here, who has read Anna Karenina? You have read it, right? Or tried to read it. It's huge. Do you remember the first line of the book? It says, anyone remembers? It's like one of those things that people remember first line of the book without having read the book. No one?
It was the best of days.
Yeah, good guess. So my three, I'm going on a tangent. I will leave this page for the math so people can catch up. My three favorite first lines of the book are Anna Karenina, and then The Stranger by Albert Camus, and States of Matter, the StatMech book. That you know, right? Boltzmann killed himself. Ernst Fest killed himself. Now it's our turn to kill ourselves. That is so famous that even Elon Musk tweets it like every other month. And he has not read the book for sure. We know that, right? And he literally tweets this thing like every 2 or 3 other months when he wants to look intelligent. Albert Camus, anyone knows the first line of The Stranger? No one? You know, I thought maybe you had read it. I don't know why I thought that.
It's too hopeful for me.
Huh? He's too hopeful.
Yeah, it's too hopeful.
Well, the first line does not sound hopeful. The first line is mother died yesterday or maybe day before yesterday. I don't remember. And Anna Karenina, the first line is all happy families are similar in their own way. All unhappy families are different. So my long story comes back to like all equilibrium systems are kind of the same, you know. All non-equilibrium systems are very different. We have no guiding principle. And this 1 over square root of n is a sign of equilibrium. If you're seeing that your noise by signal is not dying as 1 over square root of n, that means something is wrong in your experiment. Either it's not equilibrium or your independent observations are not independent, right? There is some correlation between them. So this is like a fundamental test which shows up for any extensive quantity that you can think of, right? For any ensemble. We saw it for canonical ensemble. We saw it for grand canonical ensemble. In your homework 3, I'm basically telling you all the problems that are going to show up in homework 3, and it's going to be very, very basically 1 or 2 new problems, but otherwise it will all be same. We will show something even more interesting. You will show that the variance of n can actually be written down explicitly, and it looks like n bar square multiplied by kBt divided by volume multiplied by kappa. This kappa is the isothermal compressibility. Rigorously, it is defined as minus 1 over volume by partial derivative of volume with respect to pressure at constant number and temperature. So if you can measure, so this is once again an example of the fluctuation dissipation theorem. Remember, we got a similar relation for sigma E square, right? For sigma E square, there was a bunch of term over here, but there was another thermodynamic observable that showed up. Anyone remembers that? Heat capacity, right? So heat capacity is something, how do you measure it? You measure the heat capacity by pumping some heat into the system and seeing how much heat does it take to change the temperature by 1 Kelvin, right? Compressibility is type of the same thing. You measure how much pressure do you have to apply to a system to compress it by a certain volume. But you can measure the compressibility by just observing the number of fluctuations in the system, which is kind of crazy, right? It's not obvious at all. So this is once again an example of fluctuation dissipation theorem. It keeps showing up again and again. And Chandler talks about it in one of the latest chapters. We will get to it at a very later stage, probably. Any questions about this? Okay, so you'll be doing this derivation in homework.
Question which is unrelated, but can we think of an MPT in ensemble? And then, can we?
Sure. NPT.
Yeah,
Oh yeah, in my research group, people do NPT all the time.
yeah, so my guess would be like, if we do the same derivation, but then like the energy would be replaced by entropy, is it?
No, which state function has natural variables NPT? Nate Gibbs. Listen to Nate.
Yeah, but like because when the sum, like with some of the microstates,
Yeah.
so it's just that enthalpy part, the entropy. is-
Yeah. But the math will be similar. The P nu will be a bit different. Yeah. So, but you can do that's why Chandler actually stops after canonical. Chandler says now you can generalize it to whatever you want, right? You can think about, yeah, you can go crazy. You can define all sorts of ensembles, but the same math will apply. And this basic picture that whatever ensemble you are thinking of, it can be embedded in a larger system, which is microcanonical, and then use Taylor series. This basic picture applies to everything. But today, I want to talk about one more thing, which is the way a lot of StatMech books derive ensembles. They don't do it by this Taylor series picture. They do it through a Gibbs entropy picture. Ironically, Gibbs did not do it through the Gibbs entropy picture. Gibbs did it through the way we are doing it. But in the 1960s or so, it became popular, especially due to this guy named E.T. Jaynes. So it's a maximum entropy framework. And there you have a different form of entropy, which is known as Gibbs entropy. So let's look at that one. I won't be talking too much about Gibbs entropy in the homework or final. I think there will be one homework problem probably where I might ask you to show that Gibbs entropy, which we are going to do next, is consistent with other entropies, but I won't be going too much into this. So Gibbs entropy. So what is this Gibbs entropy and why do we need it? So, and Chandler talks about it, and I will write down it's a bit abstract, so I want to write down all of my arguments. So in the treatment so far, we assumed that we looked at the system and bath as a whole, right? And thought of it at equilibrium, like a macrocanonical ensemble, right? In this treatment so far, we assumed system plus bath is equal to microcanonical. And if it is microcanonical, then we can use the S is equal to KB ln omega formula, right? So when you do your undergrad PChem, it's cool when you know S is equal to K log W. And you think, wow, it's profound. I know everywhere. I know everything now. But S is equal to K log W applies only to a macrocanonical ensemble. If you have a canonical ensemble, S is actually complicated. Remember, in order to derive the S in canonical ensemble, we had to assume that the ensembles converge and things like that, right? But if we assume the total system plus bath is microcanonical, and I need my equation number, we got to 5. Then we can think about the entropy of the full thing with 0. This 0 here denotes system plus bath, okay? So I can think about entropy of the full thing, system plus bath, and I can say that this will be equal to KB ln omega 0, right? Because the full thing is microcanonical. So, oh, by the way, if this is Gibbs entropy, what is the name of the S is equal to K ln omega entropy? Boltzmann entropy, right? So just to be clear, versus Boltzmann entropy, which is this thing, okay? So for the system plus bath, we can still think about the Boltzmann entropy because it applies to a microcanonical ensemble. So now let's introduce a few quantities. Let's introduce let's say that the system is in some microstate nu, okay? And let's say that when the system is in microstate nu, the entropy of the bath is denoted by S nu bath, okay? It's just a variable. There's nothing profound about it, okay? So S bath means entropy of the bath. And on top of that, this nu over here is telling you entropy of the bath when the system was in microstate nu, okay? Is equal to entropy of bath when system is in microstate mu. Okay. Why did I write this? It's not clear at this point, but it'll become clear in a moment. So now let's try to think. So this was equation number 6. So let's try to think about S naught minus S nu bath. S naught is what? S naught is KB ln omega naught, right? Using equation 6. S nu bath. What can I do to write down S nu bath? I have already said that the system is in a microstate nu, right? So I fixed the energy of the system. If I have fixed the energy of the system and number of the system, this could be grand canonical, this means that for that particular value, the energy and number of the bath are also fixed, right? So it's abstract, but it makes sense. So I can again write down minus KB ln omega, but now I will have E minus E nu and N minus N nu. Why could I use the microcanonical formula even for the bath separately? Because I'm looking at a particular microstate of the system. That's why I could do this, okay? This thing is going to be minus KB ln omega of E minus E nu, N minus N nu divided by omega naught. Have we seen this thing before? Omega of E minus E nu, N minus N nu divided by omega naught is the probability of the microstate. That's how we derived the canonical ensemble, right? We counted how many states can this bath be in and divided by the total number of states. So this thing is minus KB ln P nu, because all of this is simply the probability of that microstate, okay? So we have just shown that S naught, and if this is a bit abstract, what I'm doing right now, Chandler goes through it in detail, so I'm following that. If it's not clear, go back and read Chandler, it'll become clear. If not, I can discuss this more again. But this is not the most important thing you take in this semester. This is to show you that the formulation that you see in books, what is that formulation? Where does this P log P come from? That's what I'm going to show you. So S naught minus S nu bath is equal to minus KB ln P nu. Okay. One more abstraction. At equilibrium, at equilibrium, average value of the entropy of the full system, at equilibrium entropy is extensive, right? So this should be equal to S nu bath averaged plus S nu system averaged. And what do I mean by average? Average means go to every microstate, calculate the probability of that microstate and calculate the average, right? Just like Nick helped us do for n square, right? We wrote summation P nu and nu square. That's what we are doing over here, okay? Therefore, S nu system averaged is going to be S naught bar minus S nu bath bar, or average of S naught minus S nu bath. Okay. Now I can use our favorite formula. We know how to calculate averages. How do we calculate average of anything? We go to every microstate, nu, we write down the thing that we are trying to calculate an average of, S naught minus S nu bath, and multiplied by the probability of that microstate. But pay attention, we just calculated S naught minus S nu bath over here. We just showed that S naught minus S nu bath is minus KB ln P nu. So if we put that over here, something very interesting happens. Therefore, S nu system bar is equal to summation nu. What is S naught minus S nu bath? That is minus KB ln P nu multiplied by this P nu. So that is equal to minus KB summation over all microstates P nu ln p nu. Or the average entropy of the system is minus kb summation of every microstate p nu log p nu. And this average entropy is known as the Gibbs entropy. This is abstract. There is no way that this is absolutely clear to everyone, or that it is absolutely clear to even anyone, because there are a few abstract things I did here. Mathematically, it's not got that complicated. What we did in these manipulations were mathematically complicated. Here, it was a bit more intuitive, okay? So let me write down the main thing that we derived here. So the final expression that we have showed here. So what we have showed is S system averaging over all microstates is going to be minus KB, go to every microstate, do P nu, ln P nu. Or we can just define an entropy that looks like, so we are going to call it Gibbs entropy. This is not just any entropy, this is Gibbs entropy, okay? Minus KB summation nu, P nu, ln P nu. And we call this equation number 8. This is Gibbs entropy. This is applicable to any ensemble. The omega E minus, here what we did, omega of E minus E nu, N minus N nu, we could have just done omega of E minus E nu, right? And then it would be a canonical ensemble. We did it for grand canonical. Omer wanted to work on NPT ensemble. We could do the same thing over here. So this formula for entropy, this Gibbs entropy, it's not the real entropy as of now. We call it the Gibbs entropy, can be written down for any ensemble. In your homework 3, in the next problem, I've basically created your homework today, you will show that Gibbs entropy is consistent with Boltzmann entropy in every possible way. I will ask you to look at a few consistency conditions, and you will say it follows all the nice things that you expect it to follow. Okay? It is extensive, it has nice monotonicity properties, everything, you will see all that. So a lot of StatMech books start with this formula for entropy. They say, this is the formula for entropy. Don't worry. How did we start? We started by the Callan approach. We said, if there exists equilibrium state, and if you're isolated, there exists an equilibrium function, function entropy, right? And we started StatMech also by that. We said there exists S, and which has all the nice properties, and all microstates are equally probable if a system is isolated. And then we started from there. Many textbooks, such as Macquarie, which is very popular in StatMech, does not start with that. Macquarie starts with Gibbs entropy and derives everything out of this. In order to derive other ensembles, so in Macquarie's book, what they will do to derive other ensembles is to take this Gibbs entropy and add Lagrange multipliers, which enforce, for example, the number to be the same as the average value of things like this. And then they do the math and they show this Lagrange multiplier is equal to chemical potential and things like that, right? So you're welcome to go and read that approach. That is a second way to derive ensembles. We don't do that over here. So this is a second way to derive ensembles. This is not the only way to derive ensemble. There is a third way to derive ensembles. The third way to derive ensembles, you have to go to YouTube, as for many things. You have to go to videos by Leonard Susskind, who is a professor at Stanford. He has this set of lectures. You are nodding your head. Do you know the name of his lectures?
No, but I know who it is.
It's like a minimum, it's called the minimum basis to physics or something like that. And he has videos, theoretical minimum. So he has a set of lectures called theoretical minimum. And there he decides the ensembles in a very nice way, and you see how things show up. So that's the third way to do it. At some point, you will realize it stops being rigorous, but that could give you intuition into why these ensembles are this way, okay? So, but Gibbs entropy is one way of doing it. Now, in information theory, in electrical engineering, there is something known as Shannon entropy, which looks just like Gibbs entropy. It's minus P log P, okay? But in your homework, you will show how Gibbs entropy is consistent. But apart from that, we are not going to do anything with Gibbs entropy in this semester. Any questions? Okay, so I want to take 10 more minutes and set up what we are going to do starting next week. So right now we have just finished for those of you who came late, the first part of the semester, we have defined three possible ensembles. We calculated the microstate probabilities of those ensembles. I connected those ensembles to thermodynamics. And then I told you with sufficient amount of algebra and partial derivatives, you can do whatever you want, and get variances, averages, third moments, everything. You have the machinery. Okay. We have set up the machinery to use statistical mechanics. Now we will actually start using it. So for those of you who play classical music, this is like, I have showed you how to read the sheet music so far. Okay. I have not done anything else. It's not the boring part. It's actually quite interesting, but the part that starts now starts to become more interesting because you see how it is very, very powerful and how the application of these ideas allowed people to solve really, really fundamental things. For example, the heat capacity of an insulator behaves as cube of temperature at low temperatures. The heat capacity of a metal behaves as linear in temperature, and we will derive all those things. Black body radiation has a T⁴ dependence. We will derive that and all sorts of things. In order to do that, so we are starting the next part now. So part 2 of this course, part 2 of Chem 687, which is non-interacting ideal system. Sounds very boring, but it is actually very interesting because we will also throw a little bit of quantum mechanics into it. So those of you who here has never taken any quantum mechanics? Margot, have you taken quantum mechanics? You're an applied mathematician. You have not, right? So it will look a bit funky, okay? Quantum mechanics is always funky. The first time you read it, the second time you read it, the nth time you read it. So I will point you out to other articles, and I request everyone else to help Margot in that, okay? In the final exam and in the midterm, I will never assume some quantum knowledge. For you, I will try to state whatever is quantum, but it will help you if you have some understanding of quantum. And why do I say that? Because technically this course has prerequisite PKM and thermodynamics, right? So there is a bit of a disadvantage if you have never taken quantum mechanics, but you are not the first math student to take it. Luke also took it and he survived, better than survived. So you'll be fine. The craziest thing about quantum mechanics is that the energy levels are quantized. Okay. So if you are sitting in a chair and I start, or let's just go with me, and I start pumping some thermal energy into me, if I'm a classical system, I will keep oscillating more and more and more, right? Quantum mechanics says you will not just keep oscillating more and more and more. You can oscillate only at quantized levels. Your energy can increase with very small increments. So this concept of quantization will show up more and more. Okay, and we will work through it. So in order to do this, I have to set up a few things, very basic. First thing I want to talk about is why the name partition function. You already got a sense of this. You used it already because you know Helmholtz free energy is. Go ahead.
Would you oscillate even as quantum system any way possible if you don't have restrictions?
Yeah. We'll get to that. But it will be quantized. Most quantum systems, the energy values are not continuous, right? There's a discrete spectrum. That's the basic idea we will use.
Step goes to 0.
In some limit, right? You can always go to 0 in some limit, but we won't get too technical in the quantum, okay, in this course, but we use just a small amount of quantum. So in fact, for those who are not comfortable with your quantum, and if you have not taken it, the only thing that I would like you to look up, there are two things you should look up. One is particle in a box. Solving Schrodinger's equation for particle in a box. What are the eigenvalues and how does it look like? And the other one you should look up is quantum harmonic oscillator. For quantum harmonic oscillator, you will see that the energy eigenvalues look something like n+1/2 h-cat omega. I don't care if you can derive it. In fact, Hermite polynomials are one of the things that I hate very, very much. It's terrible. If you like ladder operators, you can go and refresh all that, but we are not going to use any of that. We will use these type of solutions. So it's a good idea to look up and read on particle in the box, what are the energy eigenvalues for that and how does it work? And how does quantum harmonic oscillator work? Okay, the solution for that. So Wikipedia, even Wikipedia has articles on these, and that's in good detail. And I recommend reading up on that. So now let's come back to why do we call partition function as partition function? And this could be the canonical partition function, which we wrote down going to every microstate and doing e to the power minus beta e nu, or this could be the grand canonical partition function, which is going to every microstate and doing e to the power minus beta e mu n mu. So why do we call it partition function? So the way to understand it, let's just look at canonical to give this intuition. The same thing applies to other ensembles also. If you have a system where the energy can be written as the energy coming from two subsystems, subsystem 1 and subsystem 2, where the microstates nu1 fully characterize the subsystem 1 and microstates nu2 fully characterize the subsystem 2. This could be two independent particles, right? If you do this, and if you think about Q, it's going to be summation nu e to the power minus eta beta e nu, summation nu1 nu2, because nu is just microstates, right? E to the power minus beta e nu1 multiplied by e to the power minus beta e nu2. And these summations can be done separately. So you can have summation nu1 e to the power minus beta e nu1 multiplied by summation nu2 e to the power minus beta e nu system 2. So what did we just see? It's as if the composite partition function of Q12 is a product of the partition function of 1 multiplied by the partition function of 2, right? It partitions in a product. That's the whole idea here, right? So if you have independent systems, the partition function is a product. And we already know this for a canonical ensemble, right? Because K, it's related to Helmholtz free energy, which is extensive. So this is not surprising result. So this is why we call it partition function. So if you have n atoms, which is what we are going to have over here in our non-interacting ideal systems, we will have n particles, right? And they don't talk to each other. They are independent, right? So if you want to calculate the n particle partition function, that is just going to be calculate the one particle partition function and take its power n, right? So non-interacting ideal systems are quite easy. All you need to do is to look at one particle at a time. And if you can do that correctly, then you just have to take its power and you get everything. When we get into quantum mechanics, we will start to worry about 1 over n factorial. And in this last midterm, you worried about all of it. Alex is still worrying about it. So I won't say anything much except that don't worry too much about it, okay? If your answer depends on n factorial, your problems will not be graded depending on how your answer changed with n factorial or not, okay? I will not be taking that into account. So this is going to be true for independent n particles. The particles could be electrons, the particle could be bosons, the particle could be phonons. The quantum mechanics comes and makes things complicated, right? When you do your quantum mechanics, you have, or the other thing I should write down over here is Pauli exclusion principle. So these three things from quantum mechanics will be, actually, I will write one more, which is the uncertainty principle. That we already use kind of when we talked about calculating volume in phase space, right? We divided by h cut. So these four things are the quantum mechanical things that you should know. There might be a few more that come up later. If they do, I will tell you. But if you have ever taken chemistry, this is freshman chemistry, right? This is the first thing they do, I think, in freshman chemistry. If I'm wrong, then in PChem 1, PChem 2, it's definitely done. I did not take chemistry, I did engineering, but I was still covered this much in the basic intro to chemistry in the first year engineering course. So you can cover that. Wikipedia has articles on all of this. Just read Wikipedia, you will be up to snuff. So we are going to use this to calculate partition functions. How are we going to set up the problem? in order to set up the problem, let's say we have n indistinguishable particles. So this is important. We are going to work with indistinguishable particles. We are not going to work with distinguishable particles, okay? And indistinguishable particles where each particle can be in an energy level epsilon 1, epsilon 2, epsilon 3, epsilon infinity. There is an infinitely many levels of energy. And maybe they are continuous. Maybe they are not discretely separated. Okay, maybe we will generalize it. But for now, let's think about discrete value things. So, for example, we did something like this earlier in the problem that we did in class, right? We had a two energy system, right? Two state energy system, 0 and epsilon. Now I'm generalizing it. I'm calling 0 as epsilon 1, then epsilon 2, epsilon 3, so on and so forth. So for example, two level system with n particles, you would have particle 1 in either the ground state, which is epsilon 1, or the excited state, the epsilon 2. So let's say the particle 1 is in the excited state, right? Particle 2 could maybe have been in the ground state. I don't know where it is, right? You could do something like this. So the microstate of such a n particle system with energy levels epsilon 1, epsilon 2, epsilon infinity, n, and it's important, very, very important to note here, n indistinguishable particles. If they were distinguishable, what I'm going to do next will not work. It's only for indistinguishable. Can be described simply by writing how many particles do we have in the epsilon 1 state? How many have energy epsilon 1? How many have energy epsilon 2? How many have energy epsilon infinity? Does this make sense? It does not matter which one of those have energy and energy epsilon 1, right? Why? They're indistinguishable, right? If they were distinguishable, then we would have to count whether it's Kinjal sitting in energy 1 or whether it's Vanessa sitting in energy 1, right? But we are assuming Kinjal and Vanessa are indistinguishable. That's in quantum line, that's okay, you know. They are not quantum, as we know, as we hope. So you know, graphically, it would look something like this. You could draw your energy levels just like I did over here, but now you have many, many energy levels: epsilon 1, epsilon 2, epsilon 3, epsilon 4. And in each one of them, you're counting how many do you have? N1, N2, N3, N4. And you go up to epsilon infinity, and you have infinity, N infinity over there. Okay, here's a question for you. In any given microstate, if I wanted to count the total number of particles, how would I get it out of these small n's? Add them up. That's N1 plus N2 plus N infinity. Let's write it down a bit more elegantly. We go to every, we are not talking about microstates now, we are talking about energy levels, right? So we go from energy level 1 to infinity and count small nj in that, okay? This was easy. Now let me ask you, how about the energy of a given microstate? What would that be? Let me give you some hint. We are again going to go from j is equal to 1 to infinity. What should I write over here?
E into N.
Yeah, the voice on the Zoom is correct. Nj multiplied by epsilon j. Does that make sense? That is the energy. If everything was in ground state, then the energy would be N1 multiplied by epsilon 1, right? And where N1 would actually be equal to N nu because everything is in ground state. So this here is total number of particles in a microstate, and this is the total energy of a microstate. Now, if you are going to work with a canonical ensemble, n nu will always be constant. You are forcing n nu be equal to n. But if you are working with a grand canonical ensemble, n nu can fluctuate, right? So it's a very general setup. The last thing I'm going to tell you over here is the name of these n1, n2, the small n1, n2. They are known as, let me write it down on the next page. I will repeat this new equation. So we said the microstate can be characterized as n1, n2, n infinity, where this is number of particles in energy 1, in energy epsilon 1. If you were doing a fixed number of particles, what range can small n1 take? If n was fixed, what is the range for small n1?
From 0 to
It can be between 0 to capital N, right? Maybe all particles are in ground state, or maybe all particles are having a big party and they are in the highest excited state. Go ahead.
My mind doesn't work properly this morning, but how can we account superposition between states?
Oh, it will all happen. It will all happen. Yeah, you're getting there. You're getting there. Your mind is superimposed with the future class. You're getting there. So these N1, N2, N infinity are called occupation numbers. And in this topic, which I'm starting now for next, we will be close to Chandler in this, although Chandler does, what will take me 2.5 hours, Chandler leaves in one homework problem, which is kind of terrible. So these are called occupation numbers. The last thing I want to tell you is two very special type of particles for which these occupation number take two very, very special values. It turns out for electrons, or more generally, particles that are known as fermions, any particular nj can take only 0 or 1. That's you start getting your hint of superposition. Quantum systems, if it's an electronic system, in any particular level, you can only have one electron.
But you have to for the spin, right?
Yeah, we count the spin separately, so that's fine. However, there are a bunch of particles, and examples of those are phonons, photons, etc. These are more generally known as bosons. And here, the nj can take any value, 0 or 1 or 2, it can go up to infinity. Fermions follow a particular statistics, which we will spend some time studying, which is known as Fermi-Dirac statistics. So for fermions, we will be very interested in calculating the average. What do we want to solve here? We want to calculate the average number of particles in a given energy level, given what we know about the system, okay? For bosons, the statistics that they follow is known as Bose-Einstein statistics. And this Bose is not Bose, it's not like Jose. Bose was from, anyone knows where Bose was from? Yeah, what was his name, full name? No, Satyendranath Bose. That's a good one though. J.C. Bose was also a very good scientist. S.N. Bose was this Indian scientist who derived all of this. But this was colonial era, he was like, no one would publish his thing and everything. And he sent it to Einstein, and Einstein was like, holy crap, this is incredible. So, and then he published it together with Einstein. So Einstein kind of got like kind of freeloaded onto it. He had also thought of it, in parallel. So he sent like a letter to Einstein saying like, oh, dear Professor Einstein, I have found these things. It looks very interesting. So we'll be studying all of this. So we will start this next week. I'm going to take So Chandler goes into all of this in an abstract way, which is actually very easy. The math of all these Bose-Einstein and Fermi-Dirac is very easy. Next week, on Monday evening, so Thursday there is no class, Monday evening, I will be talking about the heat capacity problem, which really involves phonons, which involves a particular type of bosons. So I will be doing some practical applications, lots of heat capacities, and then we will come back to the algebra, the abstract algebra of Fermi-Dirac and Bose-Einstein. And if you have not given your midterm, you can drop it over here. And don't have discussions on Slack about midterm. Alex has not turned his in.